Here is also a efficiency trend prospect by ITRPV. ITRPV is International Technology Roadmap for Photovoltaics. And this is new data, ITRPV 2014. So ITRPV is predicting the efficiency improvement like this. For a conventional P-type multi-crystalline silicon solar cell, they are predicting the efficiency is limiting at 18%, something like that. And for P-type high-quality multi-crystalline, and for P-type mono-like silicon, the efficiency level is roughly 21%. But for N-type mono and back contact cells, they're predicting commercially available efficiency of 25, 26, but no idea to improve further the efficiencies. So our approach is very important because we are aiming to achieve the efficiency 30% or more than that. Okay, so nextly, I'd like to talk about more detail our project, Future PV Innovation. Future, I mentioned several times, the future stands for Fukushima Top Level United Center for Renewable Energy Research. Good naming. And JST selected this logo anyway. The catch copy, the main subject is silicon nanowire solar cells. This program continued 5 years from 2012 to 2016. And I'd like to talk about again why nanowire solar cells. Two motivations. One is a band gap control, and the second is a ultra thin type silicon solar cell. For controlling band gap to the level of 1.3 to 1.7 electron volt, we need to make very thin or narrow silicon layers. And if we succeed to control the band gap energies to this level, we can use this material as top cell absorber of all silicon tandem solar cells. And in the future, if we can improve this material, for example, to the level of gallium arsenide single solar cell, single junction solar cell, we can improve the efficiencies probably 28% level for single junction solar cell. But in the initial stage, we use this material as top cell of tandem solar cell. And the second motivation is ultra thin type silicon solar cell. At present, the open circuit voltage of 0.75 volt has been achieved by Panasonic and other research groups, but those open circuit voltage is limited by bulk recombination. So to improve further the open circuit voltage, we need to reduce bulk recombination. Bulk recombination means OJ recombination when the material quality is improved. So that's why to improve further the efficiency of silicon solar cell, we need to make silicon layers as thin as possible. But silicon is a typical indirect transition material, so photocurrent decreases with the decrease of thickness. So enhancement of optical path length is very, very crucial to improve the short circuit current. So to improve the absorption of thin wafers silicon, we use a wire structure to optically confine. This shows a silicon quantum dot solar cell versus silicon nanowire or nanowall solar cell. In the project, I have already tried the quantum dot superlight structures, and we achieved open circuit voltage 0.65 volt under 20 cents. But under this program, we focus on silicon wire or wall structures. Dot and wires have advantage and challenges. Advantage and challenges are so quite different for silicon quantum dots, superlattice, and nanowire and nanowall. But based on those achievements, we use some of those processes to wire and wall solar cells. Here is our band gap energy as a function of diameter of width. Diameter or width. This circle corresponding to a quantum dot structures, and this shows a quantum wire and quantum walls. So, if we use a quantum dot for a diameter of 4 nanometer, we can get 1.65 or 1.7 electron volt. For wire structures, for 4 nanometer diameter, 1.5, and for quantum wall, 1.2 or 1.3, something like that. We need much thinner layers for a quantum wall, but wall has several advantages. So that's why we are trying to prepare wire solar cell and wall solar cells. Okay. Up to now, if we check the literature, we have so many pioneering papers up to now, from 1960 to up to now. These are papers published previously, but they are preparing wire structures or wire solar cells, but diameter is 0.1 micrometer, something like that. So we try to make much smaller sized structures. Okay. So this is a theoretical efficiency of tandem solar cell. And if we combine, for example, 1.7 wide gap material with 1.1 silicon solar cell, we can expect more than 30%. This shows the final images of device structures we are aiming. We use a wire solar cell or wall solar cell as top cell, and as a bottom cell, we use a conventional or heterojunction silicon solar cell. So by combining these two solar cells, we achieve more than 30%. Here is also a theoretical calculation with emphasis on open circuit voltage. And for device analysis, we use this model. We assume the wire structure passivated with aluminum oxide, and we calculated open circuit voltage as a function of thickness. The junction is formed like this, P and N. And with reducing the thickness of wire structures, the open circuit voltage improves. This red shows bulk silicon solar cell, but for wire solar cell, the open circuit voltage is strictly limited by surface recombination velocity. So for a surface recombination velocity of 10 to the 4th centimeter per second, we have no advantage preparing this type of solar cell. But if we can reduce the surface recombination velocity to 1 centimeter per second level, you can expect very high open circuit voltage, but for 20 or 10 micron in thickness. So that is a very challenging target, but we try our best to make this ultra thin type solar cell. But however, we need to use wire structures because optical confinement. Silicon is an indirect transition material. For 10 or 20 micron thick solar cell, the current level dropped very rapidly, so we need wire structures anyway. I know that there are so many issues to overcome to meet the challenging target of 30% efficiencies. We have to tackle those issues, how we prepare wire structures, and whether we can control the band gap or not, and how the absorption is enhanced by using those wire or wall structures. And also, in device physics side, we need to propose a new device structure, how to make junctions, how to make electrode, and what is the device physics for nanometer size devices. We need to develop novel passivation techniques and carrier transport and tandem configurations. Anyway, it's rather difficult to prepare junctions for nano-scale wires from the beginning. So our group are trying to prepare junctions by using not nano but micro scale wire or walls. That is a very realistic. Here is a research organization of future PV innovations. At present, we have 30 to 40 members here in Koriyama, and Tokyo Tech, our group, and also Yamada, Miyajima, Ihara, Kurokawa, Iwai supporting very strongly this activity. In addition to Tokyo Tech, from academia side, Fukushima University, Nagoya University, NICE, Tokyo University of Science, and NIMS are participating. In addition to that, we have several cooperating universities. And from industry, Panasonic, Kanika, and Mitsubishi Electric working together with us. And we have very strong support from international teams. So from this team, today, 6 people are attending. And of course, we work together with AIST. Here is a future PV innovation research structures. I'm research director, and Ichikawa-san is the deputy director. And we have 3 teams and 1 technical support teams. The team 1 leader is Professor Nakajima, and for team 2, Associate Professor Miyajima, and for team 3 again, Dr. Ichikawa. And we have small groups like this, but we are working together. And also we have so many people from abroad, and this solar mark is international advisory committee members, and the rest are postdoctoral fellows we are hiring under this program. We have several from China, Thailand, Vietnam, and Pakistan, so Ukraine, like that. We have so many foreign researchers. In addition to that, we have also the 20 Japanese researchers. And here's a research schedule for PV innovations. This program was initiated July 2012, and roughly just 2 years have passed from the beginning, and already midterm evaluation was made last month, and up to now we hired this number of postdoctoral fellow and technical assistant. And in year 2012, in the beginning of 2013, we set up the equipment at each institute, but we moved those equipment to Koriyama, and at present, all equipment are set up here in Koriyama research centers. And we have 3 years more to conduct R&D. In addition to those R&D, we already organized the PV science school, so-called Rika Kyoshi in Japanese. The first one was held last year, and this year in September we have the second one, and we continue with this activity, and also we have international symposium, this one.